The inductor or coil is an electronic component capable of storing energy. So far we have seen how a battery can store energy by chemical reactions, and also how a capacitor can store energy by generating an electric field. The inductor does not use either of these options, but stores energy in the form of a magnetic field. So in this episode we will learn how an inductor works. Inductors work thanks to their spiral shape, which takes advantage of a mixture of three rules or laws that relate electric currents to magnetic fields. So let's analyze each of these separately, and then we will see how they work together. The first of these was discovered by Hans Christian Ørsted, and it states that an electric current, namely the movement of electrons through a conductor, is capable of generating a magnetic field. And it is because of this dependent relationship between both characteristics that the term electromagnetic field is also commonly used. One way to remember the direction of this electromagnetic field is to use the right-hand rule, in which if we point our thumb in the direction of the current, then the direction in which the rest of our fingers point will be the same as that of the magnetic field generated. But be careful in this part, because although in most of my videos I represented the electric current with electrons, which have negative charge and move from the negative pole of a voltage source to the positive pole, since we could say that technically it is more correct, in this video we will use the conventional current direction, that is to say depicted positive charges moving in the opposite direction. It is not a big difference, but it does affect the result when applying the right-hand rule. The second law is Michael Faraday's law of electromagnetic induction, which tells us in simple terms that the variation of a magnetic field can induce a voltage, as we saw in the chapter on electrical generators, where moving a magnet in a cyclic manner near a wire generated an alternating current. It should be noted that when Faraday's law mentions a variation of the magnetic field, it does not refer specifically to a variation in its position as in the example of the generator, but it can also be a variation in the strength of this magnetic field. We will see why this is important later on. And thirdly, we have Heinrich Lenz's law, which tells us that when we generate an electric current by means of a magnetic field, as in the case of generators, the direction of this induced current is such that it generates a magnetic field that opposes the magnetic field that generated it in the first place. Now that we understand this, we are ready to see what actually happens in an inductor. When we make a current pass through a conductor in the form of a spiral, this current will generate a magnetic field, which at first, when it goes in the straight part of the conductor, is not so strong. However, as it rotates around the spiral, the magnetic field generated in each turn will add up, since they all go in the same direction. That is, we can represent the sum of the magnetic field of all the turns as a single stronger magnetic field. And this is where Faraday's and Lenz's law comes in, and things get interesting. Since this magnetic field does not appear instantaneously, but grows gradually, we will have a variation of a magnetic field over time, which according to Faraday's law will induce a voltage, but not just any voltage. According to Lenz's law, it will be a voltage that will oppose the electric current that generated it in the first place. In other words, as the magnetic field is growing, there will be a resistance to change, but once it reaches its maximum size of force, this resistance to change will disappear completely, because Faraday's law only applies when there is a variation of the magnetic field. At this point, when the magnetic field is constant, we could say that the coil will act as if it were a simple wire. But when we cut the current, the magnetic field will begin to lose its strength, that is, again we will have a variation in the magnetic field, which according to Faraday's law will induce a voltage, but this time, since it is decreasing, the direction of the induced current will go in the other direction. The result of all this is that in spite of having cut the initial current, which was fed by a battery or something of the sort, for a few brief moments we will have a current induced by the magnetic field that we had generated in the coil. And this is precisely why an inductor is said to be able to store energy in the form of a magnetic field. Now that we understand how a coil works, let's see what effects it generates in a simple circuit. Pay special attention to the behavior of the lamp in each of the stages. When we close the circuit, the current has two possible paths. However, due to the initial resistance of the inductor, most of this current goes through the easier path, namely through the lamp. However, once the magnetic field of the inductor is stabilized, and it starts to behave like a simple wire, with virtually no resistance, the easiest path will become that of the inductor and the lamp will turn off. After this, when we open the circuit and the current is cut off, the magnetic field will lose its strength and will induce a current, whose only path is to the lamp, so it will turn on again. Of course, this will not last forever, because the lamp will act as a resistor that makes it difficult for the current to pass through, and also because when the electrons pass through the inductor again, they will have to fight again with the resistance to create a magnetic field, and the cycle will continue until there are no more electrons moving, and the magnetic field in the inductor has lost all its strength. If we make measurements of both the voltage and the current passing through the inductor throughout this cycle, we will find the following behavior. We have talked about how inductors work, but we have not talked about how to control the effect of the inductor in the circuit where it will be located, or in other words, how strongly each inductor opposes changes of state. This property is known as inductance. It is usually represented as an L in honor of Henry Lenz, and its unit of measurement is the Henry, in honor of Joseph Henry, who was another scientist around the same time who devoted himself to the study of electromagnetic phenomena. This unit can be described in many ways depending on how we want to use it, but in general terms it is a value that relates the effect of the current applied to the induced voltage and the magnetic field generated. The inductance of a coil depends on several parameters, so let's analyze some of them. The first and perhaps the easiest to understand is the number of turns that the wire will give, because in each turn the current that passes is generating a small magnetic field, and the more turns we have, the more of these magnetic fields we will be adding to our total magnetic field, with which we will obtain a greater inductance. It should be noted that obviously this wire must be coated in such a way that the only possible path for the current is a spiral. If the wire were not coated, the current would seek the shortest possible path, and the magnetic field would never be generated. The second parameter is the length of the inductor, because in order for the magnetic fields of each coil to add up effectively, they must be as close as possible. In fact, remember this relationship. Try to think of the opposite case. If the length were extremely long, we would practically end up with a wire, which we know does not act as an inductor. Therefore, the shorter the length, or the more compact the inductor, the greater the inductance. The third and fourth parameters are directly related. They are the area and perimeter of each turn of the wire. One way to understand their effect is to think about the distance the current must travel to finish each turn. Although a constant current in a segment of wire will always generate a magnetic field of the same intensity, if we lengthen that segment, so will the magnetic field. In other words, the larger the loop, the greater the inductance. Finally, the last parameter I want to talk about is the magnetic permeability of the core. So far I have represented the center of all the coils as if they were empty. However, we can add different materials in the center to enhance the creation of the magnetic field. In simple terms, the magnetic permeability is an intrinsic value of the materials and indicates their ability to be affected by magnetic fields. And therefore, the higher the magnetic permeability of the core, the higher the inductance will be. You can use formulas like this one to calculate exactly the inductance of a coil according to these parameters. But I think it is much more valuable that you understand the reasoning behind the effect of each of them. Because of all these characteristics, inductors, or coils, are an extremely versatile element. If we concentrate on their ability to generate a resistance to current changes, they can be used in signal filters in a similar way to capacitors, or to stabilize the current delivered by a power supply. On the other hand, if we focus on their ability to generate a magnetic field, inductors can be used to move other elements by acting as an electromagnet, which is exactly what happens in a relay. Besides this, the electromagnetic field generated can also be used to induce currents in other inductors, as in the case of transformers or cell phones with wireless charging. And as if this were not enough, the inductors can also be used to heat some metals, as in induction stoves, or in more extreme cases even to melt metals. I can't promise to talk about all these options, but for sure we will talk in more detail about some of them in the future. I remind you that you can follow me on my different social networks, and that you can help me on Patreon if you think the work I do is worth it. That's all for now, and see you in the next episode.